All right, that should be live now. I can see the little sign.
Give it maybe just give it a second.
Let's see. Oh, I can see the feedback on YouTube. So hello, everyone. Welcome to tonight's talk, the last talk of the year until September. Tonight we have Sheri-Lynn Karl, who is from the British Astronomical Association and is a geophysics geophysicist, if I'm not saying it incorrectly, with an academic background in astronomy, who's going to speak to us about solar observing on a budget. If you've seen the title of the talk, she already has a fabulous picture of the sun behind her. And if you look her up online, you'll see loads of really great pictures of the sun. She's definitely the person to get advice from. And yeah, I'll let you speak. Thank you.
Thank you very much for that. I'll see if I can get the screen shared here. Hopefully this is starting to come through.
All right, it's showing up just fine.
Okay, that's great. Well, thank you very much for the invitation to come and speak to the Glasgow Astronomical Society. I've been invited to come and speak about solar observing and simple processing and looking at solar observing on a budget, because it's an area of astronomy I think a lot of people believe is quite an expensive one to get into. And I just want to show that depending on your budget, there's certain levels of this area of astronomy that you can get into. And it's a very enjoyable, very social hour astronomy, which a lot of our astronomy being dark skies in the cold, this one actually is light skies in the relative warmth. So I think solar astronomy is one of those that's quite attractive to people. So not sure why this has popped up here. There we go. Need to give you the warning about looking at the sun with the naked eye. You absolutely do not want to do that. It will cause some extreme damage if you do that. This example image is quite an old image, but it's one of my favorite ones about the warning of the dangers of looking at the sun with the naked eye, especially through optical equipment. And this is actually a grape that's been put behind the eyepiece of a telescope that is now bulging due to the intense radiation that's coming through. So it's just a good example that you don't want to have your sun unprotected when you're looking at the sun, especially if you're using any sort of optical equipment. So that's the fair warning. So a bit about the back garden observing with solar astronomy. I think a lot of times people think about astronomy and they picture having a dome in their back garden, which is very lovely. But when you're doing solar astronomy, it's not quite as essential because it's something that you can do with very simple equipment. The setup can take place every time you decide to go and look. So it's very easy. You don't need to have as precise of alignment of your telescope equipment that you would normally. So it's much more user-friendly in that sense. So this sort of setup where you've got say a 4-inch refractor or smaller is absolutely ideal, but we'll get more into that during the talk. Thought I'd start with something a bit different, which many people probably have done in the past, and hopefully some of the members may not have seen this before, but it's the art of the solography, where you're able to use a pinhole camera and record the sun's position over a period of time. So it's something that you can make on your own. Some of you may still remember the 35mm film canisters, which if you put some photographic film in there and make a pinhole camera and set it out to observe the sun over a period of time, you'll actually be able to image the track of the sun through the sky over the course of the seasons. So a good example of this, there's one that's a 4-month picture imaging the sun where we're looking at the winter period where the sun's quite low in the sky and where it's actually transiting across. And then 4 months later, how high it actually gets in the sky and how the path of the sun will then transit through. The last time I used this slide in a particular talk, there was a member from down in the Weymouth Astronomical Society that sent a picture through that she had made off Portland Bill. And this one covers from the summer solstice to the winter solstice, and you can see the entire track of the sun during that time period. So it's quite a neat way to look at the sun from a completely different perspective than many people do. You can get involved with this using a solar can. So it's already a pre-made commercial version of this pinhole camera for about £16. So not very expensive and something it might be worth trying. I was speaking with the members before the meeting started, and we were looking at the eclipse glasses or the solar viewers. And many of you may have these lying around from previous opportunities to view eclipses. And it is worth keeping these to hand because the sun is getting more active and sunspots are getting larger. They'll be visible to the naked eye. But when I say naked eye, it must be a very protected naked eye. And these are absolutely ideal for you to view the sun in comfort and make sure you don't damage your eyes. And the cost of these run from about £3 to £35, depending on if you want something that's a cardboard sort of frame or something a bit more substantial with the plastic. The reason I want to mention these in particular is coming up on the 10th of June, there's a partial annular eclipse, of which a portion of it will be visible from Scotland. So I've looked up Glasgow just so that you can see it's going to be almost a 32% coverage of this partial annular eclipse. So you'd want to make sure you've got the proper shielding for your eyes to take a look at this. And with a bit of luck, we'll have a sunny day and you'll actually be able to see the bite out of the sun during this eclipse taking place. So something to mark on the calendar. Make sure you look forward to seeing part of the annular eclipse that will be taking place on the 10th of June. Another quite simple way of looking at the sun in a very protected way, but also quite an interactive way, is using projection of the sun. When you're looking at the sun, it's the same size as the moon is that you're looking at it in the sky. So it's a half a degree across. So that gives you a good idea about what you're going to be looking at if you're naked eye. It's half a degree across. If you put your finger out, you'll be able to block it out. But when you're looking at it with telescope equipment, the aperture is not crucial the way it is when you're looking at deep sky objects. So you can use the small refractor that's been collecting dust in the corner because you're not using it for planets or deep sky, and take that out. And that's a great device to start with, is using a small refractor. We definitely recommend making sure you've got a full aperture solar filter on the front of it. If you're using the projection method, it's not as essential to do that, as long as you're making sure that wherever the eyepiece end is, it's not going to be igniting something, because you do have some very intense sunlight coming through. But to make sure it stays completely safe, make sure you've got a full aperture filter on the front of that. And I'll talk about a few options for that shortly. But what you're able to do is actually put a piece of card behind the eyepiece end, and you can then focus the image of the sun onto that card and get a magnified image to make the sunspots a lot easier to see. In these images, you can see where I was holding them, just hand holding the card and being able to get an image, and took a picture with a camera on a tripod out to the side. Nice, simple way. You can see there's fairly sharp details on here. I've seen people use music stands or other devices to hold on to the card so that you can look at it and then start to just trace where the sunspots are if you want a record of what you're looking at. So this is a quite simple way of looking at the sun. You can do some sketching and get some detail to record for your notes. There's not a lot of people doing sketching right now, so it's something that is worth actually putting the effort into. And it'll certainly help to train your eye on what you're looking at. I'll talk more about that in a minute. You can use binoculars as well. If you've got a simple, cheap pair of binoculars, that can be set up to be used in the projection method as well. You only need 1/2 of the binocular to do that. So it is worth putting a card to block out the sun so you don't have it completely overshadowing your image, and just use one side of the binocular and project that onto a card. So it's easy to do that as well. But the simpler the optics within the device, the better, because if you have compound, more advanced optics, the cements that are inside of it can melt due to the heat buildup. So it's best to go with the simplest version. So solar binoculars are another nice way to get involved with looking at the sun and using a dedicated piece of equipment. The prices I've listed on here are what they were in the UK just a couple months ago. And I don't want the prices to intimidate you, because the prices here are including the import costs and the VAT that it's always added on. So they're not that expensive if you were able to buy them at source. So some of these come from the US. It depends on where they're coming from. But this is after it's had the import duties and everything added on to them, just fair warning. But these are purpose made for solar observing, and they allow you to comfortably view the sun with both eyes in a binocular view. And I think that makes you feel more involved with what you're looking at. If you think of the number of times you may have grabbed a pair of binoculars to look at the moon and how you can really start to focus in on the detail that you're seeing, these binoculars will give you that same ability when you're looking at the sun. It's just that you'll be looking generally in the white light, so you're looking for sunspots. We'll talk about some of the features that you can see shortly. So just as an overview of what the size of the sun is going to look like, depending on which sort of image or optical device that you're using. If we use the naked eye with the protected eclipse viewers, you've got that 1/2 degree across that we're already used to. So just think of it in terms of looking at the moon with the naked eye. If you go to a sinocular, you've got that bit more magnification, just like you would use with your standard binoculars on the moon. And then if we move up to more of a small telescope, you will get a lot more detail, just as we're normally used to. But just to give you an idea, because I think that's a question that people start to think about, is what size am I actually going to see and how much detail is going to be possible. So some inexpensive recording, and this is what I like to refer to it when it comes to the sketching. So I mentioned that a bit before doing the projection method, where you can project the sunspots onto a card and just sketch around what you see, which is quite easy. But with a simple pad and you have your pencils and a little bit of ingenuity, it is great to sit there and try and sketch what you see. So I'm being a bit brave here and introducing a couple of my sketches because I'm not an artist in the slightest. But these were really made to start to train the eye to understand what you're looking at. Because I think when you just take a quick look in a telescope, you go, oh, there's a bunch of something there, but I don't know what I'm seeing. And when you try and actually sketch it, it will train your eye to know what you're looking at. And suddenly these features will become so easy to see once you know what you're looking for. So here's just a black and white sketch of a sunspot, nothing really fancy, but it's representative of what I was looking at the time. This particular one that was done with the Personal Solar Telescope, so a 40mm dedicated telescope to the sun and hydrogen alpha. I'll get into more detail about it shortly. It was quite active with the prominences of these features we're going to see kind of protruding off the limb. So we'll explain those a bit more shortly too. But here, just being able to look at the shapes and the sizes relative to one another across the disk really brings all the features to life and allows you to understand what you're looking at. And this one, which was much more recent, I actually did an image through a telescope with that one. So this is a photographic image, and tried to sketch this particular region. And it really was humbling to look at this and try and figure out, how do I draw what I see here and to understand all the variable structure that was going on. So I definitely recommend trying to do some sketches just to train your eye what you're looking at if you're getting into solar observing. So then for a little bit more money, because we were looking at some of the inexpensive ways to get into solar observing, but still trying to keep this within a modest budget. This is not observatory quality equipment. This is going to be something that you can invest in because you'll be able to use it long-term in your own back garden. So I'll focus on the white light, which most people are familiar with, our naked eye view type white light. Then also the calcium K and the hydrogen alpha, which are two of the key wavelengths that many observers are able to access from the back gardens. This is an image from the hydrogen alpha one, but taken with a monochrome camera, just to show you what you can expect in detail if you're looking at something with about a 50mm scope. So you can really get a lot of detail from a small aperture scope relative terms. So first off, I want to talk about the full aperture filter that you need for white light viewing. And the simplest and most inexpensive way to make sure you've got proper filtered optical equipment is to use the AstroSolar film. This is a mylar film that's coated to be optimized so that it lets through very little light transmission to make it safe for our viewing. It costs about 20 pounds for an A4 sheet, so there's plenty of material to work with here. You can get templates online to make the aperture fit your binoculars or a camera or any sort of spotting scope. So this is a very inexpensive way to make sure you have properly filtered optical equipment to view the sun with. This particular scope has got a manufactured version, but still with the mylar film. That one was damaged inadvertently, and a new one was made just from a yogurt pot because it fit snugly over the tube, which is very important to make sure it never blows off. You don't want it to be detached from your scope. and then the filter was placed at the end, and it fit absolutely perfectly on a little ETX70, which may be familiar to some of you. And to give you an idea of what the quality would be with the Mylar film, this annular eclipse was taken in Utah, and that is through that ETX70, just to give you an idea of what you are able to achieve with Mylar film on an already existing scope. So a standard telescope, in that sense, I'm thinking of the scope that you already use for back garden observing, or the smaller one that seems to have been discarded because it was too small for the more deep sky images you might be wanting to see. But just a standard telescope, refractors are generally the easiest to use, although as long as they're properly filtered, other versions of telescopes can be used just fine. You can buy manufactured glass filters starting at about 50 pounds, depending on the aperture. Always when you're using one of the full aperture filters, make sure that you check it before you use it every time that there's no damage or chips or any pinholes or anything that's occurred here, because any imperfections will cause it to allow light at too high of intensity to pass through and can cause damage. So always check those. If you want to invest a bit more, you can go up to a Herschel wedge, which is going to run about 400 pounds. But this really is the pinnacle of a solar filter for a refractor that just uses light baffles to reduce the intensity of the light. And that allows you to see the full solar disk without any degradation at all from a filter, and is really the nicest way and the best contrast you can see. So if you want to invest a bit more, that's really one I would recommend. It's got a built-in screen, so you can use that for finding the sun as well. So it's quite a dual function device. But either way, if you are going to get into white light observing, the one piece that I would strongly recommend is the solar continuum filter. It's about 90 pounds for a 1¼ inch threaded one that fits onto the eyepiece. You can see the green here, and that's because it's filtered for the 540 nanometer wavelength, which is the light that our eye as a human is optimized to look at. And at that wavelength, looking at the white light view of the sun, it gives you the best contrast of the features on the solar disk. And it also helps to reduce the effect of the atmospheric turbulence that we're used to. So I really strongly recommend investing in that. And even if you put a 20-pound Mylar filter on the front, investing in this continuum filter will significantly improve your view. Here's just a simple image that was taken with the DSLR camera on a 4-inch scope with the Mylar film. So it does give you a bit of a strange color tint, but once you get past that and realize that is the sun that you're looking at with the strange kind of pinkish tint in it, you can tell the quality of the sunspots. And keep in mind, this is just a single frame. So it's focused on a DSLR camera, which is not the simplest thing to focus on a telescope, as many of you know. But you are able to see these sunspots and image them with probably existing equipment that you have. And it's just a matter of appreciating it. Just needs that solar filter in the front to do that. So now looking at a few of the other wavelengths that are very accessible for the amateur. Where we were just looking at that 540 nanometer wavelength, that's going to put us smack in the middle of what we consider our white light view. A lot of amateurs have invested in the 656.3 nanometer, and this is the hydrogen alpha view. So we're moving much further into the infrared. You can also move into the ultraviolet at the 393.4 nanometer, and that's the calcium K range. So I'll take a look with these for you and show you kind of what you can expect to see and the range of the prices of the equipment. So the hydrogen alpha filter, and this is the one at the 656.3 nanometer. If you were to look through a scope that is made specifically for this wavelength, the sun is in a very deep blood red. It's quite a startling red. Your sky is black because it's only letting that one particular wavelength of light through. So everything else is blocked, and you're looking at a red sun on a black sky. Very dramatic, very impressive. And you are able to start to see these details with the naked eye quite clearly, especially if you've trained your eye to understand what you're looking at. The details will pop out at you. It's quite startling and really enjoyable. Just as an observer, it's very enjoyable. And then you might want to get into more of the imaging side of things. So hydrogen alpha telescope, one that's dedicated in that filter range, starts at about 700 pounds. So we're now looking at a leap in price, not out of range of a lot of people, but certainly to warn you, the prices do start to go up here, but they are accessible and it is an investment you can make. So this would be for a 60 millimeter scope. So you're looking at a good aperture size. It has a blocking filter because you do want to still continue to block the last of the stray wavelengths that may get through this echelon filter that's built in. But what you're also able to do is add a second filter of the same type that starts to restrict the bandpass of the filtering that's taking place. And this is quite important to understand what it allows you to see. So with just a single filter, it allows you to see in quite good detail and brightness what's happening on the limb of the sun. So all these prominences that are quite attractive to people to view, and they change very quickly as you're watching them as well, on the order of tens of minutes, for example. Just the single version, single stack of this allows you to see them very clearly. But with a single stack, the surface detail, or what I'm going to call the surface detail, it's not as sharp because you do need to have a much more restricted bandpass to be able to see these sharper. So a second filter being added will allow the surface features here to pop out. In the calcium K 393.4 nanometer wavelengths, I'm showing an example here of the Coronado. This company had made a dedicated personal solar telescope similar to the ones that you may have seen already in hydrogen alpha, and it was just for calcium. And this device is absolutely superb for the amateur. So if you're able to find one that's of decent quality on the secondhand market, it is worth investing in. It has been discontinued since Meade bought the company, which is a shame, but it's just to be aware of this one. But there's lots of other modules that have been built by other solar telescope companies that you can attach to a refractor and still get the same effect of what you have here on a dedicated scope. But unfortunately, the prices do jump to about 1,200 pounds and up. So it's something to be aware of if you want to get into calcium viewing. You are looking at a next level of price increase to do this. Now in the calcium, it's considered more of an observing wavelength, sorry, not an observing wavelength, but an imaging wavelength. Because we're looking at so far into the ultraviolet, it's very difficult for our eyes as they age and they yellow to be able to see that deep into the violet. So for example, when I first bought this scope, it was many, many, many years ago, and I was able to actually see very briefly a deep, deep violet disc, but not any details on it. But unfortunately, after a few years and the eyes finally had yellowed enough, you really can't see what's going on at all. But if you use just a simple webcam style camera, it is superb for imaging. So this is from that telescope of a 40 millimeter diameter. You can get some great detail coming out of that. So just to give you an example of where this ultraviolet range will take you. There is another way you can get into the calcium end of the range that's not quite as expensive. So on the right here, I've got an image of the sun in the calcium using that dedicated telescope. So you can see the detail. But there's also a version of a 1 1/4 inch eyepiece that's a calcium filter that is only about 240 pounds. And this one, it allows the calcium K wavelength and the calcium H, which is a 396.9 nanometer wavelength to pass. So it gives you a broader band pass of that range of wavelengths, but for a cheaper cost, which is super, and brings out the same detail. These are taken on the same day, but with very different scopes. The one on the left was a 4-inch, the one on the right is the 40 millimeter, but the detail is still visible. It's just not quite as sharp because we're not narrowing that band pass the same. But just to give you an idea, it is possible to get involved in the calcium side for a much more reasonable cost with your existing equipment. So what are we looking at? This is always the next question. You've seen these nice, weirdly colored suns. And just to let you know, the colors, because those images are taken with a monochrome camera, are colored according to however the imager wants to color them. And if you've seen images from other solar imagers, it's a purely subjective choice, usually just trying to emphasize the details that you're seeing there in some sort of aesthetic that you're bringing it towards the wavelength of what you had imaged in originally, just to give you that idea. So what these allow you to see, if we look at the sun, and everyone knows this is a giant ball of gas and plasma, we're looking at all the sorts of layers and temperatures going on here with the plasma taking place. So as we look at the sun, the outer portion of being the atmosphere that keeps getting denser and denser and denser until we get to the point where it becomes opaque. And that's our photosphere. And at the photosphere, where we look at it in white light, is where we see the sunspots. So we'll consider that the actual solar surface. And as we move up and away from that solar surface, just like as if you're peeling onion skins, but you're moving away from the core of it, you're moving up through the atmospheric layers. And those narrowband wavelengths that I mentioned allow us to see what's happening in those layers. So above the photosphere, the next layer that we're able to see, and this is using the calcium, it's going to be a bit higher up into the atmosphere, all the way up to the kind of 8,000 kilometers away from the atmosphere into the chromosphere, which was visible in the hydrogen alpha. So we can move up away from the surface and look at various structures that are taking place here. So solar features, what are these wavelengths going to allow us to see? So I've just made a short list, and I'll look at those in detail on each of the wavelengths of some examples of what's possible to see. So we've got sunspots, which you're probably already familiar with, light bridges, speculated plage, filaments, prominence, flares, and CMEs. There's a lot of other features too, but we'll look at some of the more dramatic ones visible with back garden equipment. So in white light, as you're probably already familiar with the sunspot, you've got the umbral region, which is the dark, much cooler region due to the fact that the radiation is not coming up to the photosphere from beneath. It's being blocked by the magnetic fields localized there. We've got an outer region of the penumbra, and so that's a bit grayer if we're looking at our grayscale here. So it's a little bit warmer. If we think of the solar surface as somewhere around about 5,500 degrees Celsius, when we're looking at the umbral region, it's much cooler. It could be dropping then more towards about 4,000. So you're looking at a big temperature difference, and the cooler it is, the darker it is. You're also able to see the convection cells taking place on the solar surface. And that's these little granules, or what some people consider rice grains. So this is where we're looking at those convective cells coming to the surface and then rising and descending again. So we've got little convection cells, and we're looking at it face on. So that's a really neat feature to see on the solar surface. There's also areas where you're seeing just the umbra. These are called pores. So if we think in terms of scale, those might be about 1,000 kilometers across, and then you've got your sunspots that can start extending up to planet size, for example, 50,000 kilometers across. We've got areas that may have the presence of a sunspot group, or lots of sunspots. There could be pores as a group. You could see areas where the umbra is splitting, which then becomes a very bright area with the plasma that's now very hot compared to the umbral region. So there's this light bridge. There can be some patchy areas of brightening where we've got some magnetic disturbance happening. That's called faculae. And also you may notice when you're looking in the white light that the limb of the sun actually is a bit darker. And that is an effect that is true because you're looking through a gas disk, and on the edges, the atmosphere becomes thicker, and you're looking through this obliquely, which is making it appear darker on the edges. So that is a real optical view that you're seeing there, that darkening on the limb. So these are some of the main features you'll be able to see in white light. There's another interesting effect that's worth noting is when you're looking at sunspots as they're rotating either towards you from the limb or away, is that you start to see the umbral region moving closer to the penumbral region. And this effect was identified back in 1769 and termed the Wilson effect, because what they had worked out is you're actually looking into that solar surface, and these sunspots are formed into a cone reaching within the photosphere. And if we think about a saucer as it's being turned, you can see the effect of where the umbral region will start to look like it's getting closer and closer to the penumbral region as it's moving off, because it's the top of this cone. So it's something to keep a watch for as you're looking at sunspots. So now what can we see in hydrogen alpha? So we just looked at the photosphere, or what we consider the surface of the sun. And we've moved quite a few kilometers up through the atmosphere in the chromosphere. And we're looking to see where in that part of the solar atmosphere it's going to display for us a lot of the structure of what's happening from beneath. So here we're seeing the interaction between the magnetic fields and plasma around into the atmosphere. So when we look at those active regions where the sunspots are, the umbral regions still are pretty clearly visible, but now keep in mind we're way above the surface when we're looking at these. So the magnetic field lines that are blocking that radiation coming from beneath are still causing that to be cool, and we can see that further up into the atmosphere, and that umbral region is quite clear. But the penumbral region, because it's warmer, the contrast there is not as clear because we're looking at different structure higher up into the atmosphere. So that's not quite as apparent in this hydrogen alpha view. But what we do see are the disturbances and what's happening with the plasma. So we start to see where we're going to have some sudden violent eruptions of plasma, which are flares. And this is taking place within those active regions where we'll see the sunspots and white light. We can see areas where you've got, say here, this tiny, very bright activity that's taking place. It's a really sharp, bright flare that's not going to last for only a matter of minutes. It's called an Ellerman bomb. You may be able to see off the limb, as I mentioned before, prominences where we've got magnetic field lines that are drawing plasma away and trapping it into the magnetic localized field. And as it draws it up, it just creates all sorts of different structures. So we might have hedgerows, we might have some sort of sprays. There can be all sorts of structures that that magnetic field drawing up the plasma is going to form, and we're able to look at quite easily in the hydrogen alpha view. So looking at it on the limb, you see it very bright against the darkness of the sky. Here's a planet Earth, just to show you a comparison of the scale of what these features look like. If we look at that same feature, but from the top view, looking down onto the face, we see with that plasma drawn up, it actually becomes cooler and is now a dark feature that we're looking at, and that's the filament. So a filament and a prominence are exactly the same feature, but it depends on whether we're looking at it on the limb or whether we're looking down upon it at the face of the sun. So we can see the presence of a lot of filaments. There's another sunspot, some more filaments taking place. We've got prominences. So there's a lot of detail that you can see in hydrogen alpha. And this is with the 60 millimeter scope, but with a second filter on it. So it's been double stacked is what it's called. And that filtering allows you to see in great detail what's happening on the sun. So I'll just flip back again just to show you the comparison here. So this was in 2017 where the sun was becoming a bit quieter, but back towards the last solar maximum, and it was with older imaging equipment and some older software tools. It's not as sharp a picture, but you can see how much activity was taking place back in 2013. And it's the same features with some very large filaments, some very large prominences, lots of active regions, lots of sunspot groups, flaring, Ellerman bombs, etc. So quite a bit of activity. And since we're now starting on that upslope to the solar maximum, we're hoping we're going to see something this active coming up in the next kind of 5 years or so. So now looking at the calcium K, and I saved this more to last of looking at the features because it's one that's a bit more expensive to access, but I think it's something that's very interesting. In this one, you're able to see the magnetic disturbances in quite strong detail because we've looked at the photosphere with our sunspots, we've looked at the hydrogen alpha chromosphere, and now we're looking at that onion skin layer in between that's giving us kind of a bridge view between what's happening at the surface and what's happening higher up in the atmosphere. So here, the magnetic disturbances are the strongest feature that you'll notice different from the others. And the magnetic disturbances appear white when you're looking at it here. So we've got our sunspots. You can see an active region here. The umbral regions are very clear. The penumbral regions remain quite clear. But the magnetic disturbances around that sunspot group in this white are quite strong. And you can see where that activity is taking place. There's also the plage regions where we've got a lot of magnetic disturbance, but we don't have the formation of sunspots yet. They may form, or they may just weaken and go away. But you'll see a lot of that activity that can indicate that there may be a sunspot appearing. You also might see that it's covered in these quite large plates that are on the order of about 30,000 kilometers across. And these are supergranules, or the collective of this granulation that we saw in the white light. We're now looking at large scale areas where we've got supergranulation happening with the convective currents in the atmosphere. And that's very clear in the calcium K. So always worth having a look for. So just as a bit of an active region comparison, so you can see the difference of a particular active region in each of those wavelengths. This one, where we've got a very unique looking sunspot group. I always quite like this one. But when you look at it into the hydrogen alpha side, the sunspot group, only the umbral regions are apparent. You almost have to know what you're looking for to be able to spot them. But instead, where we've got a lot of this sunspot activity taking place, it's overlapping exactly where we see this flaring taking place, and a lot more of the plasma being drawn up by magnetic fields. So we can see that there's a lot more activity taking place much higher up into the atmosphere, the chromosphere of the sun, than what we're able to see at the photosphere at that point. So you're seeing the difference. And another example here, we've got the white light image, sunspot group, the same in the calcium, and then moving into the hydrogen alpha, that same active region, there's a lot of filaments taking place here. There's some flaring. We've got on the limb some of the prominence activity. We can see a lot more of the granulation in the hydrogen alpha itself. So you're looking at the difference what those wavelengths can provide regarding how active the sun is and what's taking place between its plasma and its magnetic fields. I think the best thing about solar observing is the fact that all of these features will change on the order of minutes to tens of minutes and sometimes hours for the longest. So you could be watching something at the beginning of an observing session, and by the time you look a half hour later, it's changed. And that can be the case where you're looking at a region where you can tell there's some activity taking place. 30 minutes later, you look at it and the whole thing is flared. And you're like, what happened? How did I miss that? Or you look at images over a period of time and you might go back to an area and start to stack your images and realize you can't actually use two of the different frames from a stack because something happened in between. And it's really quite remarkable to watch. Whereas with deep sky imagers who can spend 30 hours imaging the exact same object that's not going to change, this changes quite rapidly. And I think that's quite exciting. So just another example where we're looking at more towards solar maximum, and we've got activity across the 3 wavelengths. And then just back in November, where the sun is starting to become more active again as we come out of solar minimum, you can see across 3 wavelengths again. What's interesting is before this, kind of late in 2019 and most of 2020, there were days where you could go and look at the sun in those 3 wavelengths and there was nothing. It was the weirdest blank across the sky in all 3 wavelengths. And it actually took a lot to get motivated to take pictures of nothing on the sun when you know it could be that exciting. So it is always worth looking. Something's always happening. It just depends on what wavelength that you're looking at. And sometimes, rarely, there's nothing happening. So that's kind of the whirlwind tour of some of the equipment, what you're able to see, some simple ways of recording it. And to round it out, I wanted to look at a bit more of the imaging side, because I know that's an area that many people are interested in because they do imaging in their night sky. They may have just some simple equipment already at home, or maybe looking to invest in something a bit more sophisticated, but in a very civilized type of hobby where it's during the day and you can do it on shorter timescales than you would need to normally. So for a typical session, looking at the forecast, which is important with all of our astronomy, but certainly for solar, because generally you want to do your solar observing, if at all possible, and the skies are clear, early in the day. So it's unlike night observing where you want to make sure that whatever your object you're looking at is up at the zenith to get the lowest amount of atmospheric turbulence. When you are doing solar observing, the best time is early in the morning, where you're not going to have the high altitude thermal currents that can cause problems. It's better to deal with thicker atmosphere than it is with the higher altitude currents. And the temperature of the Earth has not heated up so much yet that you're getting a lot of localized thermal currents that are taking place. So earlier in the day is much better, or immediately after rain before the Earth starts to heat up again is very good time to go out and look for the most stable views. So check the forecast. There's some resources I'll mention at the end regarding some web sites that will give you some of the current activity taking place. Generally, if I set up, it is really a matter of taking the entire tripod out, the scope out, everything comes out and gets set up every time. And when you're setting it up, it does not have to be as polar aligned as you need to do for night imaging where you're doing long exposures, because everything with solar imaging is dealing with very short exposures and movie files. So we can stack those very short exposures to get the detail that we want rather than have long extended periods of imaging. So the tracking accuracy does not have to be quite as critical as it is for night observing. So setting everything up each time, taking it down each time, it's not such an ordeal. So all this gets hauled out, set up, do a bit of actual observing at the eyepiece before setting up the cameras, and then off you go with the laptop. So I'll explain a bit more about that process in a minute. Generally, I start with the hydrogen alpha when I know that the temperatures are the most stable, because it is very sensitive to any of the turbulence in the atmosphere. The white light using that solar continuum filter is much less susceptible. So I'll do that one last, as I know that the heating of the Earth is taking place, and I'll do that one when it's going to be least affected. So there's a lot of software tools that you can use with cameras doing solar observing. And I mentioned this is going to be on a budget. So one of the best tools that a lot of the solar imagers will use is fire capture. And this is a donationware piece of software. So if you feel this is worth it to you for 30 pounds, then by all means donate that to the software engineers who designed it, because it is really a valuable piece. But you're not looking at a huge investment when it comes to the software. So here's the white light image looking through a 4-inch telescope. And hopefully you can see with the resolution, the actual granulation on the surface. Hopefully that's quite clear to everyone. What I would generally do is focus on the screen, looking at that granulation and trying to get that as sharp as possible. So there are other tools that you can use for focusing, but I find that if your eye is trained for the details on the sun, then focusing on the laptop is quite straightforward. So I'll put it at just 100% magnification, look at those details, focus on that at the periods of good seeing, and then it's all set to go. And that gives really good results. As I mentioned, you have quite short exposures. So it's best to make sure that your exposure level is low enough that you're getting a very even distribution of your grayscale and you're not saturating anything. And then boost the gain a bit higher so that you're able to see the detail that you're after. So that would be the general approach. And I usually take video files that are about 5,000 frames long. And I don't want to go really much more than that, because those features do change in that time. So it's best to keep them quite short and then use that for stacking later. So to give you an example of the seeing conditions, as I mentioned, where it's best to go observing earlier in the day, certainly before noon is preferred. And the earlier you can when the sun comes up is the best. If you look at the sun, and this is a hydrogen alpha view, if you can see the shuttering that's taking place, where we've got that shuttering or turbulence taking place very quickly across the disk, that's from localized changes in temperature. So if you set up on a concrete pad or something that's heating up quite quickly in the morning, you will notice that a lot more. If you set up on grass where the temperature doesn't change quite as quickly, it'll calm that, so you won't have quite as much of the localized effect. Around the limb, if you get the random fluctuations from the turbulence, that's from high altitude atmospheric turbulence. So that's the bit that we're trying to avoid when you're doing solar imaging. So just let you know, there's a bit of a difference between them and ways that you can counter what's going on. So go out earlier in the day to avoid the random turbulence around the limb. And also you can control a bit more what's happening about the turbulence coming across the face of the disk. So if you look at this particular turbulent one, you can see details quite well, but you can also see when it's going out of focus. But this is the actual image that came from that session. So you can do an awful lot with stacking the frames from the video file and removing the periods of time when it is poor seeing conditions. So this is exactly the image from that. I mentioned this is when the sun was quite a bit quieter. We have a little bit of features here, but not very much. So there's a few other things to watch for when you're doing the solar imaging. One of which we probably are already used to is if you've got birds flying through your images, it's always good to watch for an airplane that flies through, depending on which direction you're focusing your telescope. Because the alignment is not as sharp as you may have set up for night imaging, you have to keep watching that during your imaging session, that the disk is not drifting out of the frame itself. Depending on what your setup is between the size of the disk and the chip on your camera, you may be able to get a full disk on there, or you may only be able to get half the disk on there. You need to watch that to make sure there's enough overlap for your frames as well. So there's a few things to watch for when you're imaging to make sure you've got enough data there to do what you want with it. But there's some good software tools online that allow you to set up what your scope is and what your camera is, and you can work out what size the disk is going to be on there. And you may already be familiar with that, but I strongly recommend it if you're looking to buy new equipment that you can match them and get a full disk, because it's a lot easier to process an image with one disk than it is to start doing a mosaic of multiple frames that you may have already been experienced with in night imaging. It's a lot easier to do with one. So just for the simple processing sequence, I generally have a notebook with me, keeping track of how the equipment's behaving, as well as just sketching out quickly what features I see on there to know when I go back to do the processing, what details to look for. Always good to check for any of those actively changing features, or where you may have a flare that's taken place, or a prominence is lifted off, or you could have all sorts of things changing during that imaging session. So it is always worth having a note and looking through that. There's some really good stacking packages for software. These are also freeware ones. So I mentioned this is on a budget, and these are some of the best ones that you may have already been familiar with, but strongly recommend. The AstroStacker is superb for solar images. Definitely recommend that one. It's a freeware. AVI Stack is very good as well, and Registax. So those three are quite highly recommended, and a lot of other solar imagers use them in freeware. Once you go through a stacking process, definitely worth checking to make sure that there's no stacking artifacts that have appeared, or perhaps where it was tracking to do the stacking, you end up with some kind of artifact where it's not quite lined up. So it's always worth checking those. Once you've got the images stacked, then you can take it into a photo editing package. So I'll move on to those in a moment. So here's some example from AVI Stack. You can bring in your video file, have it, or select where you've got a frame, you know where the seeing is good, have it run through the algorithm and select what percentage of the quality of pictures that you want to keep. So generally here, I might say I want something that's less than 0.5 of a pixel shift, and just select that portion. And to illustrate what kind of improvement this actually will give you when you're selecting those best frames, this was an image after AVI Stack with white light. And once I just did some simple processing on it, you can draw out some really good detail in those sunspots and the granulation. So just to give you an idea, it may start out looking a bit soft, but by the end of a bit of processing, you can bring out a lot of detail. And I'm mentioning this in terms of the imaging, the processing, but processing solar images is so much more simple than doing night sky images. And I hope to be able to illustrate that to you in a minute. That it is worth getting into if you have been frustrated with using, trying to do dark sky images. The solar is much simpler. AstroStacker, using this software, it's got its own algorithms, and we'll go through the same sort of process where you're selecting those best periods of seeing. It'll run through the algorithms automatically. You're able to batch import the AVI files or the SIR files that you feel are the ones you want to use. Just batch import them for your white light, hydrogen alpha, calcium, for example. It'll run through the whole thing in the background for you and just spit out the images, the final frames, and you can go from there. So it's a lot of automation, which makes this quite straightforward as opposed to some other processing activities. And then moving on to the image enhancement side. So I'm going to see if I can swap over to Photoshop to give you a quick view of how this works. Photoshop is the package that I've used for years and years. And since they've gone to a subscription package, I think it's a much more affordable way, because you can take out a subscription at £10 a month, which for using such a high quality package, I think is very affordable and worthwhile. So I think that definitely is worth mentioning, whereas it used to be several £100s to buy it. Now with this sort of subscription use, it's much better. There's also GIMP, which I know a lot of people are familiar with, and that's a freeware, very well-versed package for solar processing. Lots of others on the market. It's I think looking at some of the the astronomy magazines that highlight these periodically, it's worth taking a look at those, because if you can work with night sky images, you can certainly work with solar on any of these packages. So let me just see if I can transfer this over to Photoshop.
You might need to stop share and reshare again.
Did that come through?
Oh, no, that worked fine.
Excellent. Sometimes the technology works. Right, so looking at this one, this is just a frame from a stacked image on the white light view. And I think this is quite a good one to start with. At the time, I had a camera that couldn't fit the entire solar disk onto the chip. So it's only a half. That's why we're looking at half rather than the full disk like the other images are. But with this solar processing, it's very easy to set up some actions, say, for example, in Photoshop, because you're using a lot of the same activities or the same filters or the same color setup throughout the entire process each time you do it. And as long as you set up the actions to work through to a certain stage where you'll do a final tweak at the end, you can automate this a lot. And it takes a bit of trial and error to get the right steps set up for your particular equipment. But once you do, after the stacking and you bring it into here, I can simply go to this, go to my white light, because I want white light for this one. Otherwise, I'm going to end up running it through a different filter. Go through the white light one, press go, and then I'll say, yep, that's okay. If there's anything that comes up and asks any questions, this one's not doing anything. And I've brought it to a stage now I want to do the final tweaks, and it was that easy. So if I go back to the history and say, okay, I've opened the image, you can see it's not too bad to start with, nice monochrome. And by the time I run it through my action set, I'm already to a point where I can start to do some very basic touch-ups. And if you know your tools quite well, you can simply go through and say, oh, I want to do just a little bit of sharpening. I want to just kind of darken some of the colors. I've got this one pre-set up and say, right, I know that that's the mask filter I want. And suddenly, hopefully this comes through. You can see the granulation, you can see sunspot groups, you can see macula area. It becomes very satisfying to be able to go through this on quite a short time frame. So that's a white light version. And as I sat here and did it, if I'm doing this for a real image that I hope to be able to send out to people who are interested, I might play with it a little bit more, but usually less is more when you're looking at solar images. You don't want to make them over crispy. I think that's not the technical term, but where your features are so sharp that you've introduced artifacts. And it's better if you feel you've gone to that stage, take a step back in your history, say, no, I don't think that was quite enough. And then go back and go, well, that's a bit soft. I think I will just add that extra filter and I can see what I want. But don't overdo it, I think is the key word with solar imaging. Even though you might feel like you brought out some amazing detail, you may have really introduced something that's not there. So if I jump ahead to, say, a calcium, can do exactly the same thing. I'll just jump up to a calcium set of steps. And with a quick press of a button, most of the steps have already taken place here. I might look at it and say, well, it's a little bit overcooked. Maybe I want to step it back a little, or maybe make some of the color a bit darker, make the hue a little bit different. You can do a few things depending on aesthetically what's going to bring out those features. So here I can see where there's some areas where there's some flaring that's quite clear. This active region is quite clear. You can see that supergranulation very well, etc. So one more into the hydrogen alpha, because I think this is the one that kind of intrigues people a bit more. So this one, just to show you stepping through them, I've already ran this through and stepped back, but if I go just to a few steps from starting with opening, applied a little bit of sharpening, you can see where the details coming out and also where there may have been some odd things happening with the filter. And I'm sharpening it a bit more, Looks like we're looking at a bit too much into the darks, too much in the lights. I could lighten that a bit. Start to say I want to colorize it and bring in some of the detail. And as you step through, and it looks like it's getting weirder each time, but each of these steps is now bringing it closer and closer to what I feel is going to be a final image. And I stepped it to the end. So this is just applying it to an older image, an older setup with a current workflow that I usually use. So I probably would have used a slightly different one at that time. There's some other artifacts in here which you might have started to notice, where using an Etalon filter, you start to see the discs that are appearing off the limb of using the filter itself. So you've got your sharpest, clearest, right on bandpass, and then you might have some of the ones appearing as your duplicates off to the side, and sometimes those need to be erased out. So there can be some artifacts that appear here. So I think it's definitely worth having a look at. And then just to run a final one through as well, this one's going to have a bit of that artifact that's going to have to get removed. But you can see from an opening of a file, a lot of good detail in there. Stepping through, we've got it almost to a point now where it's really getting interesting. And I want to start bringing out the features and turning it into more of the deep disk that's quite enjoyable to see. So something like that. So I don't want to make it look too easy, but just to say that once you get your workflow set up and you do processing in solar, it is a lot quicker and easier than trying to do it in night images. And I hope that brings some people back to imaging who may have given up on some of the other more difficult and long exercise imaging activities. So I think that probably brings me to just about to the end here. If I can change back to my other screen. So just another couple examples of processing, and then I would just want to give you a couple of those resources to wrap up. One resource that you're probably already familiar with is spaceweather.com. Definitely suggest going and seeing what sunspots are visible on a particular day. And if there's any feature that's active at the moment, usually they'll have some imagery from around the world with a little story added into there. So spaceweather.com is a very useful one. I always go to the University of Graz for their observatory because they have images in the 3 wavelengths that I'm interested in. So you can quickly look through and see if they are seeing activity in the white light calcium and hydrogen alpha. So I certainly recommend going to their site. You also get images of where the dome sits and whether or not they've got a good day, and they tell you what their seeing conditions are. So that one's quite interesting. And if you don't have any equipment and just want to see what's going on, this is a great one to go to. Gong, which you may be familiar with already, is a collection of hydrogen alpha scopes that are located across the world that allow us to see what's happening on the sun all 24 hours of our day. So there's always one of these scopes active that you can see what's happening with the sun. So this one's quite an interesting one to go to as well. And their resolution is similar to what a back garden observer's equipment would be. So it's actually quite worthwhile going to one like this just to see what detail they're getting. SLU, which you may be familiar with as well. That's an observatory that has several different domes and different scopes of various configurations. They do have a solar telescope. And that one, I think you can view it without having a subscription, but I do have a subscription, so I can access it anytime. But I think you're able to actually see this one on a YouTube view without it. So that one's worth going to as well. They'll just have some, the view flip between the surface and the hydrogen alpha. And if there's anything happening on the limb, they'll change it throughout the day of what you're able to see. So that one's definitely worth a look. Solarmonitor.org. That's another interesting one for looking at wavelengths that the Solar Dynamics Observatory and some of the other orbiting satellite observatories are able to look at. If you want to look deep into the ultraviolet to see what's happening, or where we've got coronal mass ejections and into also the magnetic field disturbances, worth flipping through here to see, and those other onion skin layers of what's happening in the solar atmosphere in wavelengths that we can't access from Earth. I think that's definitely an interesting one. Space Weather Live, which you may be familiar with for their information on auroral activity, they do have a whole section on solar activity as well. So that one's worth a look to see the sun in infrared and X-ray, looking at coronal mass ejections. and to see if there's any expected flaring activity or disturbances that will affect aurora here. They have it listed both on their aurora side and on the solar pages within that website. So another really good resource. And that website also has a solar cycle progression, which is why I wanted to mention it. So they've got an active solar cycle progression and sunspot monitor that will keep building, usually just on a month in arrears basis. So it will keep building this. And as you can see, we're just coming out of a solar minimum and starting into the maximum, and the predicted maximum expected to be fairly low, unfortunately. But we'll see how that comes out, because we don't have that many hundreds of years of information. So we want to see what's happening here. And this is a really good site to go to find that out. So finally, thank you very much. I hope you found some of this information interesting and useful, and happy to try and answer some questions and see how it goes. So thank you very much.
Thank you so much. That was brilliant. That was so good. And you made me realize that what I saw when I used my solar glasses was definitely just atmospheric wobble. So I'll be attentive to that next time. We have a question on YouTube from our YouTube chat from Alexander Wilson, who is asking, do the granulations on the sun change size between solar maximum and solar minimum?
I'm actually not sure if they change size because of the turbulence that's taking place, making the convection cells themselves. I have never run across information to say that they change in size. I think it's definitely something to watch. I certainly haven't noticed that imaging it. So it's a really good question. I'll have to go and look back in some of the research and see if somebody's detected that. No, thank you. That's an interesting question. I don't know.
Right, indeed, that's really interesting. I'll be cheeky and ask a question as well. You said to check your goggles or your telescope before using it.
Mm-hmm.
How would you be able to tell? Because I imagine you would have to kind of look through it. Like, would you have to see like some kind of light going through?
That's right. If you hold it up so you're able to see enough brightness coming through, so you're not staring at the sun itself, but you're holding it up rather than putting it onto your telescope or something like that first, you just want to see, because a pinhole lights can be very visible, even if you're not holding it in front of the sun. If you're just holding off the side, you'll still see if there's damage in it. So it's definitely worth holding that up, see if you see a brightness. You could even, it may not be bright enough to use it with a light bulb, but definitely take it outside where you've got the bright ambient air and take a look at through that to make sure that you're not seeing any pinhole damage or something that's going to cause light to come directly through. So that's a good question.
All right, thank you. And do you think, for instance, if we have viewing outside, we've had that actually a couple of years ago, we used the telescope that Colin has, and we were introducing the telescopes to the public. Do you think that there needs to be any kind of like training just before, just to make sure everything is safe?
It would be very wise to let everyone know, and even as they arrive, to make sure that you warn them, do not look directly at the sun because it could cause damage. I think a lot of people say, oh, I do that all the time. I look at it, but it's just glancing in practical terms is not the same as actually looking at it, trying to see a feature where you're going to have that collective radiation hitting your eyes, etc. But really, it's best practice to make sure you tell everybody when they come, you don't look at the sun with an unaided eye. You really want to make sure you have the proper equipment and to keep them protected, because the damage you can see, once it's damaged, you can't fix it in your eye. You want to make sure it's preventative. You're not going to be able to do something later. So make sure you warn them not to do that, because it's just too easy. And children are where you have to be very, very careful, because they'll try and look at a telescope, get frustrated, and they'll just turn and look straight at the sun.
Oh, yeah.
Be exceedingly careful with children if you're going to involve them in a public observing session, and make sure, if you can, get a whole pack of those sun goggles, the sun visor things, the sun goggles, whatever you've got, and make sure those are on the kids from the time they get there, and just tell them, just make sure you keep your eyes protected, for example, so they don't try and look, because they're notorious for trying to look at things because they're not used to looking through a telescope.
All right. Okay. Exercise prudence at all costs.
Yes.
Keep your sight.
Absolutely.
All right. Very good. Alistair has a couple of questions he can ask you directly.
Yes, thank you. That was a wonderful talk. I really enjoyed that. I actually, you mentioned just at the end when you were processing your images, how satisfying it is to watch them develop. Honestly, it was deeply satisfying just watching them develop. I'd almost watch that as a YouTube channel in itself, just watching you process the images and reveal the colors and details. In the same lines as what Craig has asked, and what maybe others are thinking, I was wondering, how do you align your equatorial telescope to track the sun? Have you got it sort of pre-set up so that it will track and keep it reasonably well centered?
What I've done is actually work out that the roof of the neighbor's house at the corner actually points as good a north as possible. So I've gone out looking for Polaris and doing night sky observing, actually trying to find a physical marker that's to the north. And I use that for my rough setup to make sure I can get as lined with north as possible. Using your normal mechanism of going through and doing your 3-star setup won't work. So you really need to just use north as best as you can. Make sure your tripod is as level as it can. You're trying to use the best tools that you've got. Just tell it to go through its auto setup. It's going to go through it and try and find its stars. It's not going to find anything. So I try and stick with just the 1-star alignment, and that's enough. And then you've got to manually drive it over to the sun, because many of the databases won't even put the sun in there because it's too dangerous. So you'll have to drive it over. If you're able to get one of this kind of viewing screens that can attach to the telescope, so you're able to use that to do the alignment, or else watch where you've got the shadow from the sun on your tripod to find it, so you're not looking at the sun to do it. There's a few different devices you can use, but a lot of it is either shadow or looking to see where you've got the kind of the ray of light that comes down your telescope you're seeing on the barrel itself, and watch until that gets centered and you can get it there. So the tracking that's usually with most of the computer controlled telescopes is good enough that you'll be able to do a segment of images where I can do, say, 2 sets of 5,000 frames, and I just kind of nudge it back into the center and go from there. So it's a little bit interactive in that sense, because the alignment's not perfect when you're going and setting it up all the time, but it's good enough. It's definitely good enough.
Maybe just one quick follow-up question. Yeah, you mentioned that you take about 5,000 frames, and I spotted that you were about quarter of a second on the images. So is that about 20 minutes of video, and then you just recenter it and go again?
Those exposures are all in milliseconds. So you're only looking at
Oh, sorry.
couple
Yeah,
minutes.
That's right. Yep.
Yeah,
Quarter,
they're only in
quarter of a
milliseconds,
millisecond.
so it's really only a few minutes. If you sat and watched it over 5 minutes, it'll have zoomed way away from where you're trying to center it on your chip. So it's very short times. So if I do 5,000 frames and maybe fit 2 of them in the chip size I have before it's moved off, that's really on the order of a couple minutes, and then just nudge it back. But in time scale, I'm able to set the scope up, do a little bit of visual observing, image in all 3 wavelengths, and take it all down in an hour. So it's not a long one, which works really well with the weather and how quickly it changes. So you know that if you see this gap where it looks like it's going to be good, you can really just get out there. If you've got your sequence practice, get it up, have a look, take your images, and go. It is something that is a lot quicker to do than some of the other areas of astronomy. So I think I do like to impress that upon people, because it's not something you need to spend a lot of time getting set up and waiting for your scope to cool and all sorts of things. The worst problem is actually taking a cold scope out of, say, a shed and setting it up, and you've got the sun's heat on it, and suddenly you've got dew and you're waiting for the dew to clear. So I've actually been out there with the blow dryer trying to make sure that you've cleared the dew off the lens, because it's appeared because it's too warm, not because it's dropped too cold. So it's kind of back to front when you're thinking about solar.
Thank you. Excellent.
All right, thanks, Alistair. We've got a question from Colin. You mentioned, so it's about the format of files. You mentioned .sir and .av files. What would you recommend?
So the AVI files are movie files that you're probably already familiar with other video formats. A SIR file is one that is a dedicated astronomical version that has metadata tags that you can save what your telescope type is, your camera type, a lot of the other technical information in the same file. So a lot of imagers will use that now because you'll be able to save that metadata. But as far as the actual AVI versus a SIR for quality that you get out, I haven't seen any difference.
All right, thank you. Question from Craig. Do you need an equatorial mount for your solar telescope?
No, you could use an all-azimuth mount. You can use an equatorial mount because you're looking at such, if you're imaging such short time frames, you're not worried about its tracking, because even an all-azimuth mount where it's doing its stepping, that shouldn't affect your images because it's short exposures, whereas you would see that over one where you're trying to do, say, a 5-minute or 10-minute something exposure length. So as long as it's something that can track the sun, it doesn't matter really what kind it is.
All right. Just to check, what would be an equatorial mount for those like me who are not completely sure?
So an equatorial mount will allow you to track an object as it transits through the sky at exactly the same rate that the Earth is turning. So you'd be able to position something on it and it would just continuously track it. Whereas an all-az has got one that's moving in two different, an altitude and azimuth, and it steps through. Those are kind of the two more familiar ones to amateur observers.
All right, thank you. Question from David. I've usually done most of my solar observing in the early evening. Does this have the same atmospheric conditions as morning observing?
It is quite good because you're looking at stable temperatures again. You're getting down beneath the high altitude turbulence of the atmosphere. Early evening is good because a lot of times we see that the atmosphere is settling. I think many people probably have noticed that when it comes to this time of year, about 7 o'clock or so, that things have calmed down. The sun's still high enough in the sky, and you've got much more of a stable temperature change because it's already gone through a lot of the sharp cooling before it gets to that. So yeah, that would be quite good too.
All right, very good.
I'd just say something, Laura. That's one of the things I miss about my ETX70. I had a really good solar filter, a white light solar filter, full aperture solar filter, and I had a solar continent filter as well. And this Sheri says the detail it brings out is fantastic.
Oh, absolutely, and that's a really good setup. Really,
that's something I really miss about the ETX70. Yeah, that's what it's really good for.
Oh yeah, definitely. That's why I was trying to show that one. That ETX70 I showed in the slides was my very first telescope, and 9 months later I upgraded to the LX90. So the difference in those scopes was so dramatic, and that was doing night imaging, thinking I was going to get really involved with that, and then in the end realized that no, solar is really where kind of my passion lied. So went right back to smaller scopes, but more advanced scopes.
Nice. Sinclair asked a question as well. Is it possible to use a white light solar filter at the front end of the telescope and a standard nighttime HA filter at the camera end, or is the detail lost?
The detail's lost. From what I have heard from other people who have tried that filter wouldn't work. And conversely, where the ones that you use for solar, it blocks so much you wouldn't actually get the light through at the nighttime. So they are very distinct, even though they might be looking at a similar wavelength. The way that they're operating is quite different. So from our understanding, you wouldn't be able to do that and get any of that detail out, unfortunately.
All right. Okay. And can you just so the HA filter is always the nighttime filter?
There's a narrowband HA filter that's used for narrowband imaging. And I think if those pictures from Sinclair that were shown at the beginning are stunning, where you're looking at a lot of the nebulous.
It was, yes.
View. Yeah, absolutely nebulous view. It's the same because you're looking at a difference with the sun and its intensity. Once you step it down so much as well, it's just not getting the same. The hydrogen alpha in solar tends to be an etalon rather than like a coated filter. So they are operating a bit differently. And I don't understand the engineering principles of it anymore. So I don't want to try and waffle my way through it. But certainly from what I have heard is that the nighttime view ones won't work. And I've not tried it myself, but they won't work because you're not getting to the same energy transfer in that particular wavelength. So I just know that it's not going to work, but I can't explain any of the engineering side of the way.
Okay, thank you. That sounded complex enough for me. Alistair has another question.
Yeah, kind of follow up to what Sinclair asked and what you just said. Do you have any experience of the tunable HA filters? The university had one which we used for the labs, and it was very interesting that you could tune it to see like one side of the sun very sharp compared with the other. But I wasn't sure how good it was for imaging sort of the full disk, because it felt like you couldn't really get all parts of the sun in focus at once.
The setup that I have is the Lunt version, which is a tilt tune version. So both the single stack version, the part that's built into the main tube, has got a tuning dial on it so that you're able to shift whether you're on band or off band. And also the double stack portion has one as well. So when you set it up, if it's out of alignment, you'll see what you were mentioning, where some of it's sharp and some of it's not. And it is a bit of a delicate exercise to make sure that you get them both in an equal alignment to get the same filtering across. But it's because of the tightening of that bandpass that you're looking at giving you those sharp areas. So to get them to match, and you hope to get them manufactured to match exactly, but that's a very expensive, difficult thing to do. You try and work with getting the match as closely as possible. So if you do have a particular feature that you want to get the tightest bandpass of it, then you tilt tune till you get to that for that particular area. But otherwise, if you want to look at the whole thing at an equal filtering level, then you tune it so you get an equal spread across the whole thing. So
Thank you.
I haven't used any of the more sophisticated pressure tuned ones, but I assume it's going to work in a similar manner.
I think it was a Coronado Max or something, but
Okay.
A long time ago since I last used it.
It probably was a tilt tune as well then at that time, probably.
Yeah, possibly.
Sun was up, sorry. All right, thank you very much. Well, I think we can wrap up. We've already been speaking for quite a while, so we can give you a bit of rest. But thank you. We're getting loads of thanks and encouragements through the chat here and on YouTube. I really enjoyed it as well. And yeah, and if it's okay, I could share a link to one of the websites where we can see your pictures to our Facebook page. This way, people can check out some more pictures. Do you share your sketches as well?
No.
I really liked them. I thought they were really
No.
Yeah, they were really good.
That's so cool.
No, they really are just kind of a self-eye training exercise, anything more than artistic. There's some really good people around that do some very artistic drawings that are worth watching for, but these are purely for training my eye rather than anything else.
That was great. I'll definitely look up more sketches. I had no idea that that was a thing, so it was so informative. But yeah, thank you so much. We'll be in touch by mail.
That would be great.
Have a lovely evening.
Thank you very much. It was great to see everyone on the screen there.
Great. And we can end the chat as well.
Very much for coming, Sheri, and hopefully
good to see you again.
Hopefully we'll see you in Glasgow sometime. Hopefully.
That would be good. That would definitely be good. Yeah, keep in touch. That would be nice to come by.
For sure. Well, I hope to start solar imaging again. You're giving me the taste to try it again.
Send pictures if you do. I'd really be interested.
It's mostly video.